Hello and welcome back to CB Astronomy. Today's topic is the Northern Lights, otherwise known as the Aurora Borealis. If you're from the Southern Hemisphere, it would be the Southern Lights or Aurora Australis. I may be mispronouncing that, my apologies if I am. But so there's a couple of things that have to happen for an aurora to occur. We'll start at home first, so we need a strong magnetic field protecting a planet, which thankfully we have. This is due to the iron core at the centre of the Earth rotating and generating this field. I will come back to what the field does and how it makes this happen now in a moment. But the other half of the equation is the sun. So the sun is always giving off radiation called the solar wind. Now the magnetic field can deal with this without too much of a problem, but it's when the sun emits a coronal mass ejection or a solar flare that things start to happen. So this happens when two magnetic field lines collide on the surface of the sun. Now these are caused by varying temperatures on the sun. You can see these through things called sunspots, which you can see if you have a telescope and you slap a filter into it so you can view the sun safely. Please do not view the sun through a telescope without a filter. You will go blind, and I'm not taking responsibility for you. So always use a filter. That's why they tell you in a solar eclipse as well, you need specific sunglasses because the intensity will burn your eyes out. So yeah, don't do that. But when the magnetic field lines on the sun collide, it releases a lot of solar plasma as well as really high energy particles. So these particles will travel 149.6 million kilometers in order to get to the Earth, and then it hits this invisible wall. That is the Earth's magnetic field. So the magnetic field absorbs the energy and redirects the particles to the magnetic poles, and it's at this point that the high energy particles will hit our atmosphere, and that's when the really cool, interesting stuff happens. So just imagine you're sitting at home just after getting in from work. You're going to stick the kettle on for your evening cup of tea. Say you live in Iceland for the sake of the argument, because you do need to be pretty far north or south to see the lights. But yeah, you're just after coming in, kettle's on, you stick your feet up, and all of a sudden the landscape is just illuminated with these waves of green light dancing across the sky. Like, that is just phenomenal in my opinion, and it's definitely on the bucket list to see. I haven't personally seen them yet, unfortunately, but hopefully in later life I will get a chance to. But my desires aside, we will get back on track. So where was I? Yeah, so the high energy particles will come into contact with excuse me, sorry. So the high energy particles will come into contact with our atmospheric particles. So this sends our atmospheric particles into a higher energy state, which is generally uncomfortable for them. So in order to get back down to their natural ground state, they emit this extra energy and we perceive it as light. So the colour of the aurora depends on the atoms that the high energy particles come into contact with. If it hits nitrogen, it emits a blue or purpley colour. If it hits high altitude oxygen, it'll emit a red colour. And if it hits a low altitude oxygen atom, it'll emit a green colour. Now this seems to be the most common one that occurs. So like, if you do happen to see them, you might get mostly green with hints of purple or blue or red. And personally, I think if you're lucky enough to see them at all, that it doesn't matter what colour it is, it's going to be fantastic. But so the other thing that contributes to where the aurora can be seen is so it depends on what part of the Earth is facing the solar storm and how the magnitude of the coronal mass ejection or solar flare. So for the Earth anyway, the Earth tilts at roughly 23 degrees. This is what causes the seasons to occur. But so when the high energy particles hit the atmosphere and the magnetic field, it will redirect them to the poles. It won't necessarily be even. That's what a lot of people asked, is it a even split? But it literally depends on whereabouts it hits on the field. I think the majority will go to its closest pole, so that could be north or south, and then the minority might go to the other one. But in terms of the magnitude, this can come in all range of sizes. The most recent one at the time of recording was in September 2017. The sun spat out 2 X-class solar flares, and these X-class flares are massive eruptions. Like like satellite disrupting is potentially really harmful to astronauts on the International Space Station. That's why shielding is actually a really big topic in our manned satellites. But so I particularly remember that solar flare occurring because there was talk of us in Ireland being able to see it. Now it'd be kind of the Northern Ireland parts like Donegal and what have you, but it has to be really, really strong for us to see it here, because in terms of the equator, Earth is fairly north, but like you really need to be pretty far north to see this. So like that will tell you how strong the X-class flares are, that I can get down to like a quarter of the Earth will be able to see it. Now the other thing that could let you see a solar flare is when the sun is approaching the end of its life. As it's heating up, it's going to be emitting more X-rays and more flares. So like towards the end of the sun's life, there will be massive auroras on all the nearby planets. But for the moment, I think I'm gonna leave it there for today. I know this wasn't as detailed as I'd have liked it, but that's all the information I have here for today. So I hope you enjoyed the video anyway and found it informative. If you did enjoy it, please like and leave a comment and subscribe to the channel. Links to my Instagram and Twitter are in the description, so please go and follow them as well. Have a good day, and we'll see you next time.